Good afternoon, kiddos. I am going to talk to you today about the greatest integer function. This function should just be added to your families of functions, the x squared parabola, the square root function, the rational function, sine function. It's just another function, and all the properties of algebra will apply to it. Our goal at the end of this lesson is to be able to graph and interpret the greatest integer function. So what is the greatest integer function? It's a function that's also called the step function because when you look at the graph, it looks like a big fat set of steps. So the greatest integer function notation is pretty much a absolute value, double absolute value bar or a square bracket with an extra little bar in it. So that's what it looks like, and it means the greatest integer less than or equal to x. So when we look at this function, what happens is piece 1 falls right here, and when I do this in Desmos, it does not put the open circles and the closed circles that are visibly seen. We're going to explore this a little bit on Desmos, and we will show you that when you trace this in Desmos, it shows you that, but it doesn't actually visualize it on the computer. So the greatest integer less than or equal to x. So if you have the greatest integer function of 2.7, and we take our graph and we go over 1 over 2, and right here is 2.7, we will see that our answer falls on this piece, which is a y value of 2. 2 is the greatest integer less than or equal to negative 2.7. All right, so when you look at the graph of the greatest integer function, the domain is the set of all real numbers. Because of the way this works out on the graph right here, if you take and do a vertical line, this function actually passes the vertical line test because right here we include the value, but right here that value is not included. So every x value from negative infinity to positive infinity is included in this function. The range is just a set of real numbers, so 1, 2, 3, 4, -1, -2, so on. If you apply a transformation, we vertically stretch it, we shift it left and right, and we maybe compress it. The range in the domain, or the range will actually change, the domain won't change. All right, the graph has a y-intercept at 0, 0, and x-intercepts on the interval from 0 to 1. So when we look at the first piece of this function, the parent function, and this is kind of important, I think, the first piece of this function is, sorry about this, is right here on your graph. So when I look at this right here is always going to be the first piece of the graph, and again, it will have a point at 0, 0, but no value at 1, because it's the integers less than or equal to 1. If you also come over here and look at this notation, please note that there's a square bracket on the left, but an open bracket on the right. So include on the left, do not include on the right. And the graph is always constant between the consecutive integer values. So if you look at your little steps, they are not sloped at all. They all have a slope of 0 horizontal little line segments. And the parent function jumps vertically, so from here to here, and here to here, and here to here. It's a vertical distance of 1, unless we apply a horizontal stretch or compression to our graph. But as far as the parent function goes, it is a vertical jump of 1. All right, so greatest integer function. I think the best way to think about this is on the number line. So if I have the greatest integer of -1 and I think of the number line, -1 is right here. So if I think of the greatest integer less than or equal to -1, it actually is -1. So this is going to just be -1. I know, you don't understand, but just let's give it a couple more examples, and I think it will start making more sense. All right, so if I think about the location of 1.9 on a number line, 1.9 is right here. So the greatest integer function is the greatest integer less than or equal to 1.9. So if I go to the left, less than or equal to, the greatest integer less than or equal to 1.9 is 1. All right, making a little more sense. let's tackle a negative problem. So here's -2, here's -3. So -2.3 is somewhere on this spectrum. So now, the greatest integer less than or equal to -2.3. So less than goes this way, and the first integer I run across is -3. So the answer here is -3. So basically, if you think of the number line, you're going to go to the value to the left. So the value to the left. This is also called the floor graph. You will see occasionally the notation that looks like this. Okay, so if you see, this is the floor graph, and it is the same thing as the greatest integer function. There is also something called the least integer function in the ceiling graph, but right now we are not going to go there. We're just going to focus on the greatest integer function. So, all right, so now if we start comparing these to the graph, if we evaluate the following, greatest integer function of -1 plus 1. So I'm going to tackle the graph first. If you think of the parent function, you had a piece of your parent function right here. Based on transformations, we can look at this and know that everything in my graph is going to shift up 1. So the correct graph will be in blue. So if I take this piece and shift it up 1, nothing else is happening to this graph. So what we see in blue is actually going to be the answer to the graph, or to the picture of the graph. So now if I start evaluating this graph, what happens is if I have f of -1, I am going to come over here to -1, and if I look at my graph, it is going to be -1. So the greatest integer function, I'm sorry, that's wrong. I said that wrong. It is going to be 0, because if I look at that point on my graph, the y value is 0. So if I think of this algebraically, the greatest integer function of -1, and then I'm going to add 1. So the greatest integer function of -1 is -1. The greatest integer less than or equal to -1 is -1, and I'm going to add 1, which gives me 0, which confirms my answer algebraically. All right, let's look at example B, f of 2.5. So if I go to my graph and I go over 1, over 2, over 2.5, and I come up here, this point has a y value of 3. So the greatest integer function of x plus 1 for 2.5 is going to be 3. If I tackle that algebraically, the greatest integer function of 2.5 plus 1. The greatest integer less than or equal to 2.5 is 2, and I'm going to add 1 to give me 3. And that checks out with what I got graphically. And example C, f of -3.1. So if I come over here, -1, -2, -3, -3.1's here. So if I come down here on my graph, it appears that I have a y value of -3. If I tackle this problem algebraically, the greatest integer function of -3.1 plus 1. These are the most challenging for me, so here's -3, here's -4, here's -3.1. So the greatest integer less than or equal to -3 is -4. So here I have -4 plus 1, which is going to give me an answer of -3. All right, so moving on, if I want to do this with a horizontal shift, greatest integer of x plus 2 means I'm going to move my graph to the left 2. So I think of my parent function. I had a piece right here. I am moving everything to the left 2. So you have a piece here, and then you can kind of just do your steps from there. And I think you figured out why we call this the step function. So you can do this, we'll do it analytically this time and then check it with the graph. So if I come over here and I have f of 4.5 and I substitute 4.5 in for x, 4.5 plus 2 is 6.5. So the greatest integer less than or equal to 6.5 is 6. If I go over to my graph and I go over to 4.5, 1, 2, 3, 4.5 right here, and I go up. I'm off my graph, but my next value would be here, which is at 1, 2, 3, 4, 5, 6. So that confirms what I got algebraically. All right, f of 1 is going to be the greatest integer, 1 plus 2, which is the greatest integer less than or equal to 1 is going to be greatest integer less than or equal to 1 is going to be 0. And so when I take 0 and I add 2, I get 2. So when I don't know why this isn't working on my graph. So when I plug, oh no, time out. I did that wrong. 1 plus 2 is 3. So the greatest integer less than or equal to 3 is 3. And, whoops. And if I come to my graph and I look at my graph, if I come over here to 1, I have a y value of 3. So if I look at f of negative 3.7, and I come in here and I substitute in a negative 3.7, I get negative 3.7 plus 2. I got to do that first, so negative 3.7 plus 2 is negative 1.7. And the greatest integer less than or equal to negative 1.7 is negative 2. So if I come over here on my graph to negative 3.7, 1, 2, 3.7, and I go down here to my corresponding y value, it is at negative 2. All right. Example 4, this is not in your notes, but it is in your homework. So just put your pencils down, listen, and watch. It's really not that hard. I just want you to think about what's happening as I work through this. But we have the greatest integer function of 3x plus 7 equals 15. So my answer is actually going to be a range of numbers so that will make this function true. So I'm going to set up an inequality. So when I do that, I know that I'm going to have 3x plus 7. And because we're talking about the numbers less than or equal to, that is going to give me 15. So basically, in a sense, we're just going to, if it's positive, we kind of truncate and drop the decimal. So any number between 15 and 16 will have a greatest integer function of 15. So for example, if I have the greatest integer function of 15.8, that's 15. If I have the greatest integer function of 15.3, that's going to be 15. So any number between 15 and 16 will work, but it's the greatest integer less than or equal to 15. Also, if you think about the graph, how we have the closed circle on the left and the open circle on the right. So now I'm just going to do the algebra. So I'll zip through that. So you have 8 less than or equal to 3x less than or equal to 9, divide by 3. So here you have 8/3 is less than or equal to x is less than or equal to 3. So basically any number greater than or equal to 8/3 or less than or equal to 3, when you substitute it into this problem, will give you a greatest integer value of 15. All right, so I want you to go to Desmos.com here when you are done listening to this slide, and I want you to type in the function floor of x. It is the same as absolute or greatest integer function of x. That's how we'll have to type it into Desmos. And then I want you to change the a value. I want you to see what happens to the graph here. What happens if you change the b value, and what happens here. So just as we've applied the transformation of families of functions to multiple other functions, I want you to apply them to the greatest integer function. Just see what happens to those steps. Do they stretch horizontally? Do they shrink horizontally? Do they shift up and down? Is there bigger steps between the steps? And this is where we will pick up our class discussion tomorrow. I want you to have a wonderful evening, and I look forward to seeing you tomorrow at school. Have a great night. Bye-bye.